Okay, hello everyone. Today we will learn considerations in designing experiment part 2, and probably it would be the last class for this semester. And let's move on. Chapter 12.3 is about the matched pair experiment. In many experiments, samples are paired rather than independent. One common situation is repeated observations. Why this is common? Because it's because of the expense. So when we are comparing mean difference, so here's group A and here's group B. Let's say here's treatment A and treatment B. um, it would be good to have independent samples. So independent samples of N1, independent samples of N2. However, it's all about expense. So if we use more samples, it means more expense. What if we have only 10 number of patients, and each patient get 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 treatment A first and get treatment B next? Then probably we can only have 10 observations, but we can get the difference, estimate of difference of treatment A and B with 10 observations. However, if we use independent samples, we probably need one patient for treatment A and also the other 10 patients for treatment B. So we may need 20 patients. Because of the expense, maybe the paired experiment, the design of paired experiment have benefit. So for comparing two populations, paired data can be an effective experimental design, and we may use y1 bar minus y2 bar to estimate mu1 minus mu2. Okay, let y1i, y2i denote a random sample of paired observation. So for each patient, get the first treatment first, which is y1i, and get the next treatment, which is y2i. Then we can have the paired data of y1i and y2i. And uh, and we assume that for y1i, the expected value of y1i is mu1, and variance of y1i is sigma 1 square. And for the second treatment, y2i, expected value of y2i is mu2, and variance of y2, the variance of second group is sigma 2 square. And there is a correlation coefficient for y1 and y2. In this case, y1 and y2 are not independent because it's paired observation. So we assume this thing. And let's define di, the difference between the first group and second group. Then expected value of di, which is mu d, can be calculated like this, and that is mu1 minus mu2. And for the variance part, variance of di can be calculated as variance of y1i plus variance of y2i minus 2 times covariance of y1i and y2i. And the calculation is something described in here. And when we are estimating mean difference, we will use d bar, which is y1 bar minus y2 bar, to estimate mu1 minus mu2. And for its expected value and variance parameter, the calculation is described in here. And the calculation for this thing, yeah, okay. And previously we calculated expected value of d d bar, which is mu1 minus mu2, and also we calculated the variance of d bar, which is this thing. And if we have independent samples for treatment A and treatment B, population 1 A and population B, then we will have the variance of this. And what's difference between this variance and this variance? And here's we have minus 2 low, sigma 1 and sigma 2. So if low is greater than 0, and usually since it is paired sample, so here's patient 1, and this patient 1 take treatment A and treatment B together. So many times low is greater than 0, and so which implies that in many cases, for the paired test, it have smaller variance. So the matched pairs experiment provides an estimator with smaller variance than does the independent sample experiment. That is because many times for the paired experiment, the correlation coefficient is greater than 0, so the variance estimate is smaller than the user independent sample. So you should uh, know this. And for the analysis of a matched pair experiment, we use d bar, and as is n goes large, d bar follows normal distribution with mean mu1 minus mu2, and variance is sigma d bar square, and an estimator for sigma d bar sigma d bar square is this thing, and d bar is the mean of the i's, and so we use these uh, so we use d-bar as our test statistic and employ the appropriate one-sample procedure on d-bar. And so we construct 100 times 1 minus alpha % confidence interval for mu1 minus mu2 as this when we have large sample size, and we use t-distribution when we do not have large sample size, like we have smaller sample size, like less than 30, we use t-distribution. Okay. Let's move on to example 12.2. We wish to compare two methods for determining the percentage of iron ore in oral samples. Because inherent differences in the oral samples would be likely to contribute unwanted variability in the measurements that we observe. A matched pair experiment was created by splitting each of 12 oral samples into two parts. One half of each sample was randomly selected and subjected to method 1, and the other half was subjected to method 2. The results are presented in table 12.1. Do the data provide sufficient evidence that the method 2 yields a higher average percentage than method 1? Test using alpha equals 0.05. So um, let's check first check the hypothesis. What would be the null hypothesis, and what would be the alternative hypothesis? And what we want to show is that we want to check the difference mu. Do the data provide sufficient evidence that method 2 yields higher average? So mu1 minus mu2, method 2 is higher. So alternative hypothesis is this is less than 0. And so the null hypothesis would be there is no difference. Uh, there is no difference, but the alternative hypothesis is there's a difference. Actually, mu2 is greater than mu1, and alpha is 0.05. And what would be the test statistic? The test statistic would be d bar and d bar minus 0 divided by square root of s d bar square over n. This would be our test statistic, and this will follow t distribution with n minus 1 degrees of freedom. And what else? So this is our t statistic, and if t is small enough, um, if t is small enough, like t n minus 1, 0.05, then we will reject the null hypothesis. So this is our decision rule, and let's move on to calculate the test statistic. So using R, firstly we put the input of di's, so these are di's, and we calculate the d bar, and our d bar is minus 0.01667. Okay, this is our d bar, and we calculate the variance of d here as square d bar. We calculate the variance of d bar, and here's our t statistic. Here's our t, which is d bar minus 0 square root of s d bar square over n. And so this is our t, which is minus 2.15. So our t is minus 2.159. And this is actually smaller than the this one, minus 1.79976. And so we reject the null hypothesis. We reject the null hypothesis. And what would be the p-value? So here's the t distribution, and our calculated value is minus 2.159 here, and we need to calculate area here for the p-value, which is this thing. And so the p-value uh, is 0.02 or something. Okay, this is our p-value. Let's move on to example 12.3. Use the data from example 12.2 to form a 95% confidence interval for the difference in mean percentage readings using method 1 and 2. To construct a confidence interval, we will use this formula, d bar plus minus t alpha over 2 times sd divided by square root of n. Oh, actually, in the previous example, I used the SD bar, and actually, this would be right. SD bar is actually square root of SD divided by square root of n. So maybe this notation is correct. Um, and anyway, in the previous example, we calculated d bar, sd, and so let's just calculate using r. So here d bar is here, and minus qt, this is t alpha over 2, and this is sd, and this is square root of n. So using this formula, we can calculate the confidence interval for the mean percentage reading using method 1 and 2. That is minus 0.0337, 0.0003. Okay. Let's move on to chapter 12.4, some elementary experimental designs. In this chapter, I will give you an example and um, define some definitions related to experimental designs. And uh, yeah, so let's read this example. Suppose that we wish to compare five teaching techniques, A, B, C, D, and E. So we have five teaching techniques, and that we use 125 students in the study. The objective is to compare the mean scores on a standardized test for students taught by each of the five methods. So uh, for 125 students, we want to compare teaching techniques of A to E. And how would we proceed? That's the question. So in this experimental design, how we can control gender effect. So maybe there's women and boys and girls. There might be gender effect for each techniques, each teaching techniques from A to E. There might be gender effect. Then how would we control gender effect? And also for each student, the native abilities are different. So how we can control native abilities? And also there are other factors that can affect on the results, then how we can control those factors. The answer is the random selection of the samples. Random selection eliminates possible biases, and it provides a probabilistic interpretation. And so this is what we were going to do. Let's look at the definitions related to experimental design. So definition 12.1, experimental units are the objects upon which measurements are taken. So in the previous example, individual students are experimental units. So, okay, and let's check the second definition. Definition 12.2, factors are variables completely controlled by the experimenter. The intensity level distinct subcategory of a factor is called its level. So in the previous example, experiment have a single factor with five levels, A, B, C, D, and E. Teaching techniques can be a factor. Mm. So teaching technique is a factor with five levels. Okay, and let's check definition 12.3. A treatment is a specific combination of factor levels. So in the previous example, uh, each level of the single factor represents a treatment. Um, so for A to E, each level A to E represent a treatment. Okay. And let's move on to definition 12.4. A completely randomized design to compare K treatments is one in which a group of n relatively homogeneous experimental units are randomly divided into K subgroups of size n1 to nk, where n1 plus n2 plus dot 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 nk is n. All experimental units in each subgroup receive the same treatment with each treatment applied to exactly one subgroup. So this is the definition of the completely randomized design. And for the previous example, if we proceed our design like this, the proceeding experiment for comparing teaching method A to E uh, entailed randomly dividing the 125 students into five groups, each of size 25. This is an example of complete randomized design. So if we do uh, Uh, if we proceed like this, then this would be complete randomized design. So there's teaching technique A to E. So and we have 125 students. We randomly select 25 students for each treatment. So A, B, C, D, E. So we randomly select 25 students for teaching technique A, 25 for B, 25 for C, 25 for D, and 25 for E. If we randomly divide our students like this, then this is completely randomized design. Definition 12.5 describes about a one-way layout design. And a one-way layout to compare K populations is an arrangement in which independent random samples are obtained from each of the populations of interest. So what would be the example of one-way layout is like this. Suppose Suppose that we wish to compare 5 brands of aspirin, A, B, C, D, and E, regarding the mean amount of active ingredient per tablet for each of the brands. Then we should need to take independent random samples uh, from the each populations from each brand. So it is an example of one-way layout. So here in the definition, one-way layout to compare K populations, 5 populations in the example, is an arrangement in which independent random samples are obtained from each of the populations. So each of the population of A to E, we need to take random samples from each populations. So this is different with the previous example. We are dividing 125 students in 5 randomly divide 5 different uh, groups. But in this one-way layout design, we have 5 independent populations, and we take samples from each of 5 different populations. That's the difference. Let's move on to definition 12.6. A randomized block design containing B blocks and K treatments consists of B blocks of K experimental units each. The treatments are randomly assigned to the units in each block, with each treatment appearing exactly once in every block. So what this means, I will give you an example. We are interested in comparing the effectiveness of 4 treatments. Suppose that 8 subjects are to be randomly assigned to each of the 4 treatments. So here, let's say these 8 subjects are 8 patients. So we have 8 patients, and to test the effectiveness of 4 treatments, um, we can, so this is patient 1, and for patient 1, we have treatment 2 first, treatment 1 later, and after that, we take treatment 4, and then treatment 3. Uh, so this is randomized block design. So here, each patient is a block. Um, and the treatment assigned differently. So for the patient 2, get the treatment 4 first, and then treatment 2, treatment 1, and treatment 3. So this is an example of a randomized block design. Suppose that the stimuli were applied, so the last stimulus always produces a lower response than the first. So when we get the drug, when we get the treatment 1 to treatment 4, and let's say our treatment is stimuli, and the respond to stimuli, probably the last response would be lower than the first. So for the reaction on the stimuli, the first one would have higher response. However, if since we get many treatments, probably for the last stimuli, we may have lower response. So we should consider the order of the treatment that received. So in this case, Latin square design would be appropriate. So this is 4 by 4 Latin square table. So here, what we can observe is that each row you can check that T1 there's one treatment for each treatment um, for the first row it appear once. So T1 appear once at uh, uh, block 1, and T2 appear once in block 2, and T3 appear once, and also T4 appear once. And the same thing is true for the second order, third order, and fourth order. Each treatment appear once in that corresponding row. And so in this means the treatments are balanced. And with this design, we take same number of observations in each block. So with this Latin square design, we may have 3 observations for here, 3 observations for here, 3 observations for here, like that. So if we have 3 observations for each box, then we may have 4 times 4 times 3 number of samples. So yeah, and also, what if we have different number of um, treatments? So in this example, we have 4 number of treatments. What if we have 3 number of treatments? In that case, we also need to create the 3 by 3 Latin square table. So T1 here, T1 here, T1 here, like T2 here, T2 here, T2 here, and T3 here, T3 here, T3 here. This is another example of 3 by 3 Latin square design. So if we have three samples, then you can use if you have 3 treatments, you can use this 3 by 3 Latin square table to construct your um, experiment. Okay, thank you very much for your attention on this class. And uh, as you may notice, this is the end of the chapter, and also this is end of the semester. And as you may notice, there are 4 remaining chapters in the textbook. Um, Chapter 13 is about the analysis of variance, 14 is about analysis of categorical data, 15 is non-parametric statistics, and 16 is Bayesian methods. However, I cannot cover all those subjects because of the limitation of the time. However, in our university, we provide independent courses for them. We open non-parametric statistics and we open Bayesian statistics courses. So you can probably learn more detailed knowledges from those independent courses. So don't worry too much about that. And last thing that I'd like to say is just thank you everyone. And because of the coronavirus, um, uh, we cannot meet in class, but I hope that everything get recovered soon, and in next year we can meet at the class again. I hope that. And yeah, that's it. And see you around at the campus. Thank you.